now the last two for today is we're going to look a lot at how the periodic table is arranged, many different ways that it's arranged and the information that we can learn from that. And then we're going to spend the rest of the time talking about valence electrons. So hopefully for some of you, valence electrons, you've heard this term before. And if not, it's okay, but I hope it's somewhat of a good review. So the periodic table. I love a good chemistry joke. This is how they made it. It was a giant game of Tetris. I know you're all wondering. Anybody played Tetris before? Tetris is such a good game. I hope Tetris isn't dead. Yes, it is. We got my grandmother a Game Boy one year for Christmas, and the only game we got her, sorry, I'm pulling the chat up so I can see. The only game we got her was Tetris. That woman played Tetris. Her screen time was probably just completely unmoral and unethical, but she had really good records, so I can never beat her. This is not obviously how they made the periodic table, but it would be cool if it did come together that way. Okay. Sorry, I'm getting a question in the chat. My family plays it every year at Christmas. Like what, a giant game of Tetris together? How do you play a giant game of Tetris? Oh, I did get a question in the chat. Sorry, I'm just seeing this. Do you make outlines for your exams? So somebody asked me about a study guide, and I do have it on my to-do list to put together somewhat of an outline. Actually, next Tuesday, we're going to spend some time coming up with an outline, okay, to help you prepare, okay? So we're going to do that. I know I wish it fell differently, and gave you more time, but we'll do that next Tuesday as well. Another question from the chat. Do we take our exam on February 11th during our lecture time or anytime like our quizzes? You will take it during your lecture time, okay? I used to make it all throughout the day. You could get on and take it when was convenient for you, but we ran into some issues with that. So it's going to be all the same time, just like if we were in person in class. You'd show up and you'd all take it at the same time. And that's the way we're going to conduct it this semester. So we will not have live Zoom lectures on exam days. You will all log on to Blackboard at that time and all take the exam at the same time. Okay, will we take turns with each other? Oh, and it's kind of a picture, I got it. Wasn't there one nerd guy who like predicted a bunch of the elements before we even knew they existed? I'm sure there were many nerd guys, Keegan, who did that. But I don't even know. That would be a long history of, we're not gonna get into that. Okay, periodic table. So there's several, like I said, several ways it's organized, things to know. There's like 118 elements or so roughly on it. And you do not have to memorize the elements, all right? But I do want you to know how to look at the table and extract information. So the first way we can extract information is understanding there's two main ways it's organized, two main pieces of organization. And that's highlighted in the purple and the red sections, okay? The purple section we call a row, or you might hear the word period. Okay, so if I'm going to count the rows on the periodic table, I'm going to come over here to the left-hand side, and I'll count them like this. Row 1 has 2 elements. That's hydrogen, and over here helium is also in row 1. And then you go down, and row 2, and row 3, and row 4, so on and so forth, okay? So there are 7 rows total, 7 periods in the periodic table. So if I say row 1, row 2, I need you to know what I'm talking about. If I tell you the first element in row 1 or the first element in row 4, I would want you to be able to identify that element. Okay, the red section is called a group. You might also hear the word family. And obviously it's a vertical section, so it's a column as well. So group or family are the words I use. I use the word group most, but family or column as well. So that's the red sections. Now, obviously hydrogen is still part of this red section over here. It's part of group 1, but it's also different from the other elements in group 1. We'll get to that later. So just keep those things in mind. If I say group 1 or if I say group 10, okay, you should be able to count over and identify that particular group. All right, now the ones highlighted on this are just different groups. We've got 4 groups that are highlighted, and these have common family names. All right, I'm not going to tell them to you just yet because I want to look at a few more broad scale organizational pieces. But we're going to learn the common family names. I expect you to know the common family names for all 4 of these groups, okay? All right, so that's just a little, we'll come back to that. All right, another way you can organize the periodic table is these blocks, okay? We're not gonna get too heavy into these blocks. Mainly, we're gonna talk about the red and the blue colored sections. So everything colored in red, we call main groups. Any element in those red sections is a main group element, all right? And then the blue, anybody know what the blue section's called?
Metals.
Yes, transition metals. Okay, transition metals. So those are all metals. They're different. The transition metals are slightly different from main group metals, but they're all metals nonetheless, but we'll also examine some of that later. Okay, green. Anybody know what the green section's called? Lanthanides and actinides. All right, we are not going to really spend any time talking about the lanthanides and actinides. What we just said is probably the most we'll talk about those elements. But they're down here. Notice this arrow. So these lanthanides and actinides are actually tucked up in here between these row 6 and 7 elements. They're part of row 6 and 7. But for space purposes, printing purposes, that would make a really long periodic table. So they just kind of pull them down just to keep things spatially a little easier. But anyways. Okay, another way it can be organized, oh my gosh, this is so many, is these yellow, purple, and blue sections. And I think if anybody has the hard copy of the textbook or online, if you open up that first cover of your textbook, you will see this periodic table. I think this is how it's colored. So we have yellow, purple, and blue sections. The yellow, all those elements are metals. Okay, any element that's yellow is a metal. All right. So notice any of these things over here in main group 1 and 2, these are main group elements, but they're also metals. And then we have this whole other section that were the transition metals. They are also metals. And we'll discuss, like I said, more how main group metals are different from transition metals, but they're all metals. Purple, anybody know what the purple section's called? I'm looking at the chat. Purple is, these are called yes, Summer, metalloids. Okay, what is a metalloid? These are elements that they look a whole lot. They have a lot of shared physical properties with metals. So they look like a metal, they might be brittle, they can conduct electricity, but their chemical behavior more so matches that of a non-metal. Okay, so they behave more like non-metals, they look more like metals, all right? That's metalloids. And then blue, guess what? These are non-metals. Okay, so these things at environmental temperatures, at room temperatures, are gases or liquids or solids that are not metals. Okay. All right, so notice hydrogen's kind of an anomaly because it's really over here on the left side of the periodic table where the metals are, but it's a non-metal. All right, so just keep that in mind. Okay, now we're going to get to the common family names. So group 1A, the common family name of group 1A is the alkali. Alkali metals. Okay, now notice technically hydrogen is not boxed in here. It is part of group 1, but it is not a metal. All right, so when we're talking about the alkali metals, we're just talking about lithium, which is Li, down to francium, which is Fr. Hydrogen's not a metal, so we can't technically say it's an alkali metal, but it is just organized to be part of group 1. And there are reasons for that. All right, and notice too, it says 1A. What's the A about? Okay, well, if we look here, as you go across the periodic table, you see certain things with A and certain things with B. Anything with A, if you scroll back up here, these are your main groups, okay? That's what these lines are pointing to, the groups that have A. Okay, also over here, notice all these are the main groups. So A just denotes that that column is considered a main group. And I'm going to explain more what that means. It has a lot to do with valence electrons later on. But right now, just know that's a main group. Group B, these are your transition metal groups. Now, obviously, as you go across the periodic table, yes, if you count all of them, there's 18 groups. But if you're just counting main groups, there is only 8 main groups, okay? So that's what the A means. All right, what you need to know about group 1. These elements are highly reactive, okay? So in nature, they bump into things, they're gonna react. And because of that, we don't find them in nature as a pure element. They're usually always bound up with other things in compound form, okay? So we find these in compounds because they're so reactive. All right. I'm actually going to show you 2 videos of different elements from group 1, different metals that react with water. Okay. So I'm going to stop sharing my screen real quick. We're going to look at right here on the periodic table. We're going to look at sodium and potassium. We're going to look at how these things react with water. They're very short videos. So stop share and we're going to reshare with my desktop. And right here. Okay, can y'all see this YouTube video? I might turn the sound on. I'm not sure. I used to have a different video I would show for this. And in fact, these links are right here. Oh, wait, you can't see my iPad. Sorry.
Piece of sodium metal. We notice that it's also coated over with an oxide coating. Group 1 metals become softer as you go down the column. The sodium is much easier to cut than the lithium. As we cut off the oxide layer, we can see the shine.
So pause really quick. He just cut this metal with a knife, okay? I bet that surprised some of you. Usually we don't think of metals as that malleable, but group 1 metals are really soft. And what he mentioned is as you go down, they become softer and softer and softer, okay? You can see they're shiny, they're soft, so let's continue.
Shiny metal underneath. It coats over very rapidly with a layer of oxide.
I'm gonna skip over what he's about to do next. I don't care about the electrode thing. So I want to see how this reacts with water.
To water. We notice a much more rapid reaction with the water. Like lithium, the sodium is less dense than water and floats. The metal moves across the surface, being pushed by the hydrogen gas that is produced. As you go.
So I don't know, this reaction really is, again, I used to show a different video that showed you a little more of a reaction, like a really big hunk of sodium tossed in a pond, but you still see that the reaction is moving, things are happening, that metal keeps moving across the water because it's reacting with the water, okay? If you had a bigger piece of sodium, you might even get somewhat of a pop or a boom as it hit the water and reacted, okay? So now that's sodium. Goodness gracious, sorry. Okay, here is a reaction with potassium in water. Okay, it's really quick. I'm gonna probably show it twice.
Yeah, ready? Yeah.
Okay, now how many of you know this would be much more fun if we could do all this in person? But yeah. One more time.
Ready? Yeah.
All right. So that one was way more fun. So we're going to come back to my iPad really quick. Where is it? Up here, share to iPad. So I want you to think about what were some similarities and some differences that you noticed between these reactions. Anybody have any thoughts on that? So sorry, this was the link I was talking about. I used to show this link, but I went to find it earlier today and it said invalid. So you just Google YouTube sodium with water and you can find several different examples. But what were some similarities? What were some differences between those 2 reactions? I'm looking at the chat. The potassium seemed more explosive when it contacted the water. Kendall said that. Bailey said they both had reactions to water, but one was more intense than the other. I agree. So which one was more intense? Kendall said the potassium was more explosive, okay? So potassium seemed to react, I noticed it reacted quicker, okay? That explosion was pretty immediate. The sodium did react with water, but again, it just wasn't very explosive, a little less entertaining. So let's look at group 1 for just a second. So what if, I'm gonna ask you a question. What if I dropped a piece of cesium into some water? What do you think would happen? Okay, Summer already answered that question. The further you go down in that group, the more intense the reaction would be. Okay, so you think it'd be more explosive, more immediate, more instantaneous. And then francium probably even more so, right? And you're correct. As you go down, these metals become even more and more and more reactive. It has everything to do with the size of them and their electrons, and we'll talk about that more in a minute. But just notice there's a trend, okay? It's kind of what I wanted to point out and what I wanted you to get from this. All right, so that's main group 1. Any questions with main group 1 for the time being? So this might be a dumb question, but if these elements are so reactive, why don't they have that sort of reaction in our bodies if we are mostly made of water? That is because they are not in pure form in our bodies. They're like never in pure form, okay? They're always combined in some sort of molecule or protein, or they're already ionized, which is a word that is all about chapter 3, okay? They've already given away an electron, okay? So there's a reason for that. The answer to that question really is going to be fully understood once we've talked about chapter 3, Keegan. But they're never alone in their natural form, just coming into contact with water. They've already reacted, or they're already part of a compound when they enter our bodies. Thank goodness, right? Okay. So the rule for today, what you just learned is don't ever go eat a solid piece of sodium metal or potassium metal. All right, main group 2. The name here is very similar, okay, but don't get it confused. It is alkaline, L-I-N-E, earth, metal. All right, alkaline earth metal. So here we have like beryllium, magnesium, calcium. You're actually probably very familiar with magnesium and calcium, right? We need these things in our diet. I know when I was pregnant, I would take magnesium supplements. Some of you may take different supplements and vitamins. These are things we certainly need in our bodies. And similar to group 2 or similar to group 1A, these are also highly reactive, but they are not as reactive. So they are reactive, but less reactive than group 1A, main group 1, all right? Less reactive than main group 1. So it's very common to also find these not in pure form, but reacted with different elements in compound form in nature, okay? All right, we're gonna move on to the next group, group 7A. Does anybody know the common name for group 7A? They're boxed in red over here.
Halogen.
Yes, thank you, Jonathan. Halogens. Okay, so you've got fluorine, chlorine, bromine, iodine. These are your common halogens. We call them 7A, and here's what you need to know about them. They are colorful, corrosive nonmetals. So most of them are gases or liquids at room temperature. And corrosive, what does that mean? Okay, something that's corrosive eats away at things that it comes into contact with. And think about this. If we put any of these elements with hydrogen, look at what we have. HF is called hydrofluoric acid. Hydrofluoric acid. HCl is hydrochloric acid. HBr, hydrobromic acid. HI, hydroiodic acid. These are all acids, all right, when they're paired with hydrogen. But just to indicate, we know acids are corrosive, and by nature, these elements eat away at things. So another thing to know is that they commonly react with group 1 metals to form salts. Can anybody name a very common salt between a group 7 and a group 1 element? NaCl, okay, which is crazy. When you take chlorine, which is can be a corrosive element, and you put it with sodium, which is a metal we would never want to ingest by itself, now suddenly we have something we eat every day in our diet. Isn't that crazy? But to broaden your horizons for a second, any combination of group 7 and group 1 is called a salt. So for example, if we had lithium with fluorine, lithium fluoride, that's a salt. If we had potassium with bromine, potassium bromide, that's a salt. Okay, so any combination of these elements, a group 1 and group 7, we just call it a salt. If you actually want to watch the reaction for sodium metal with chlorine gas, it's really impressive, and it forms this very docile white compound, right? Salt. That's the link for it. I think it will impress you. Okay, that's group 7. Group 8A, common family name. Anybody know? I bet somebody knows what these are. Group 8, the ones boxed in. What do we call these? Yes,
Noble gases.
Kendall said it. Noble gases. All right. Okay, I'm going to ask you guys. I bet some of you know. Why are these called noble gases? What's so noble about them? What do we know about the noble gases? Okay, I'm seeing 8 electrons, 8 valence electrons. Good, that's true. So we can go ahead and write that. They have 8 valence, even though we don't know what that is quite yet. Or we may know what it is, we just haven't talked about it. What kind of characterizes these though? Like what about their chemical behavior? So far we've talked about 3 groups that are pretty reactive. Jonathan said it in the chat. They're not reactive, okay? Non-reactive. They are what we call inert. That's supposed to be parentheses, inert. Okay. They don't tend to react with other elements. Okay. They don't do much. All right. So anyways, keep that in mind. That's because they have 8 valence electrons, but we'll explain more on that later. So we have the common family names now. Now I want to talk about this phrase right here. Because as we've seen, there's so many different ways the periodic table is organized. There's a lot of thought put into this. The further that scientists have studied it, they've realized there's more trends than we may think. And so periodicity is just a systematic trend with a certain property. All right, I gotta turn my space heater off. Hold on. All right. So a certain trend. So the first trend we're going to look at, you're going to have to turn your head sideways, but if you zoom in, we're going to talk about atomic radius. Okay, what is that? Obviously, radius has to do with the size of something. If you think about geometry, when you have a circle, okay, the middle of the circle, let's say it's here, the radius we know is the distance from the edge to the middle, okay? It's half the diameter. So if we're talking about an atom, this is a decent drawing of an atom. Okay, you got the nucleus right here in the middle. I'm just going to write the nucleus. And then we know, we looked at last week that electrons are in this bigger circle around the nucleus. We call it the electron cloud. So you got electrons out here. And those actually, we even said their role is they contribute to the size of an atom. So the way we measure atomic radius is due to the electrons. And as we plot that out, so if you increase an atomic number, we got all the atoms here, or most of them. We don't go to 118, but it's close. As we go across atomic number, you can see the sizes are plotted out. And what do you notice? You notice these peaks or these spikes in the graph every so often. So let's look at this. What elements are at the top of each spike or peak? What elements are these? Yeah, they're all group 1A. Okay, so these are all group 1A, main group 1. All those metals we just talked about. Now notice again, hydrogen is part of group 1, but again, it's kind of doesn't fit very well because it's not a metal, and obviously it doesn't follow the trend here. So these are the group 1As besides hydrogen. So what does that mean? All of these tend to have a larger atomic radius. Okay, they're bigger. They're some of the biggest elements on the periodic table. Okay, which elements are at the bottom of each dip? Minus hydrogen. What elements are these that I just underlined? They are the group 7A, right? So these down here are the halogens. So if we had to come up with the trend ourselves, I want to make a statement about this. Let's go down here. We're going to draw a trend in atomic radii. So draw yourself, if you have a blank slide, I don't know if I gave you one. Draw a little periodic table. No applause, please, hold it. We're gonna draw a trend here. As we go, okay, group 1 is over here, right? And group 7 was over here on the right. So as we go from group 1 to group 7, what do you notice? What happens to atomic radius? I'm gonna abbreviate. Atomic radius does what? Increases or decreases?
Decreases.
Yes. As you go across the periodic table, atoms get smaller. Why is that? Does anybody have a guess on why that happens? Well, let's go back up to the periodic table. I'm going to zoom in on just some random row. Look at these numbers. I haven't even mentioned this. These numbers are organized by increasing what? What are these numbers? 40, 40, 41, 42, 43 as you go across. Atomic number, which is the number of protons, remember, in the nucleus. So as you go across from left to right, atomic number increases, which must have something to do with the fact that atoms are shrinking. They're getting smaller. So let's look again at a simple drawing of an atom. Here's the nucleus. Or I'm going to actually draw it like this. I'm going to draw, you can see that there's protons in there, okay? So as you go across, we are adding more protons to the nucleus, okay? And remember that there's electrons out here, and because there's a positive negative charge attraction, those electrons that are flying around in the atom, they're attracted to the nucleus. They feel a pull towards the nucleus, but they're always moving so they don't fall in or suck into the nucleus. But because we increase in protons as we go left to right, guess what that does to the atom? It shrinks it down. Not by a lot, but enough to say that there's a trend, okay? So that's why it decreases as you go across. What about if you go down each row or each period? As you go down, and I'm not just talking about group 1, this also is seen in group 7 and group 8. What happens to the atomic radius as you go down? Well, we have to learn something else about an atom. As you go down in row, we have to add, I call it layers of an onion, okay? You have to add a layer. So this would be a good drawing of hydrogen. Why? Because it's on row 1, or helium. We got one layer around or one electron cloud layer around the nucleus. But as you get to row 2, lithium, and any element on row 2, you got to add another layer representing row 2. As you get to row 3, guess what? You have another layer. So what do you think is happening to atomic radius as you go down? Okay, because you can have electrons on any one of these rows. And we'll talk about this a little more in the coming slides, but atomic radius increases because we are adding different layers which correspond to the different rows. Okay, so what you can know overall is that down here in the bottom corner, just kind of a generalization, these are the largest elements on the periodic table, and these elements up here by fluorine are the smallest. All right, so there's the trends. Questions on that? Okay, so I will mention there was another trend up here. I'm not going to really get into it for time's sake, and it's not that it's not important, but melting point, there is a trend with melting points in atoms and elements, but it's just that this trend is a lot less pretty, you can see, but it's still there. But I'm gonna kind of skip over it for now. The main one I wanted you to know was trend in atomic radius, but there's other properties as well that have trends. Okay, so that's it for the periodic table. I want you to know how it's organized. If I ask you to, like if I picked out 4 different atoms and I said put them in order of increasing atomic radius, like from smallest atom to the biggest atom, knowing these trends, hopefully you could do that. Okay, there's some practice problems at the back of chapter 1. You could practice those. If I said put them in order of decreasing size. Again, knowing these trends, that's the kind of question I could ask to test your comprehension of what we just talked about. All right, valence electrons. So we've actually already mentioned it a little bit, but to break down what a valence electron is, I'm first going to start with talking about the fact that atoms have energy, okay? And the energy is found in the electrons. So I'm going to write this. The arrangement of an atom's electrons determines its chemical properties. Or you could use the word behavior, okay? It's chemical properties or it's chemical behavior. So this word arrangement tells us electrons are not free to move wherever they want to go in an atom, okay? For example, if you have this picture, what you might have thought last Thursday when we were talking about this is that electrons are just in here and they literally can just fly around wherever they want to go, okay? That's not the case. They have certain locations they can be in, certain locations they can't be in, okay? That's kind of what the next blanks down here get at. Their arrangement is determined by specific locations and energies that are associated with those locations, okay? Atoms have energy due to their electrons, and electrons have certain places they can and can't be. Think about the difference with this, a good example. Think about the difference between a ramp and a set of stairs, okay? A ramp and a set of stairs. Let's draw that out real quick. I'm gonna come up here. If we have a ramp, okay, there's my ramp. You can be at any height along the ramp. You can stand at any point and be at any height, right? I could stand down here and I could be at this height, or I could stand up here and I could be at this height. And guess what? I can be at any height in between, depending on where I stand on the ramp. A set of stairs, you can't, okay? A set of stairs, you have certain heights you can be at, certain heights you cannot be at. So I can be at this height, okay? Or I could be at this height, but I cannot, I'm gonna put a black X to indicate I cannot be at that height, right? I can't stand in between the stairs. So that's the way it is with electrons. They cannot be at any point. It's not the ramp analogy, it's the stair analogy. And those stairs, if you think about that, kind of corresponds to these different energy levels. An electron could be on energy level 1, energy level 2, 3, or 4, and it goes all the way up to 7 because there's 7 rows on the periodic table, but they can't be in between. And I think I just mentioned it, but I want to label these circles that I'm drawing the electrons on. We call these energy. The actual word they use is shells, energy shells, okay? So this would be the energy shell 1, and this would be energy shell 4, okay, as you count. All right, questions so far about this? Now, I know you're thinking, what the heck does energy shells have to do with me being a nurse or whatever? And I promise you, okay, sure, maybe you're not going to study electrons for the rest of your life. Don't do that. I hope not. I hope you have a more exciting life than that. But all of this stuff is really, really foundational, and it's really, really important for understanding how things behave, why chemicals and why compounds do what they do, okay? Why water is a liquid at room temperature, at Earth's livable temperatures. All has to do with electrons and its properties at a molecular level. So I promise this stuff is important for why things behave the way they do. All right, so let's talk about a valence shell electron now. Okay, so we've been talking about electrons, but what is a valence shell electron? It is an electron in the outermost energy shell. All right, so if we go back up to this picture right up here, which electron is the valence? It would have to be this guy, right? This would be the valence. And you could draw more than one electron. There could be many electrons on the valence shell, but in my picture, I just had one on each, so. Okay, so I want to reinforce the point that valence shell electrons, they matter for explaining how certain elements behave the way they do. We're gonna look at these 3 elements right here, fluorine, chlorine, and bromine. And we've already decided, and we know we've talked about how they're all a part of main group 7. They're all part of the halogens, okay? And they're all corrosive. Why are they all corrosive? Why do they share that common property? It all has to do with the fact that they have the same number of valence electrons. We're going to look at this. Let's draw a picture of fluorine. I'm going to draw my nucleus for fluorine. And how many energy shells should I draw for fluorine? How do you know? You look at what row it's on. What row is fluorine on? How many layers to my fluorine onion or atom should I draw? 2. Okay, Keyshawn says 2. So boom, boom. There's fluorine. Now, if fluorine has some valence electrons, we need to know how many. Well, how do we count valence electrons? I was actually going to do that on the next slide with you, but I think it's important here. You count valence electrons the same way you count main groups. I'm going to say that again. You count valence electrons the same way you count main groups. Can you count main groups? Anything with an A beside it, remember? A denotes it's a main group. If you can count those, you can count how elements have valence electrons. So any element in group 1, all of these and further down, these have 1 valence electron. Any element in group 1A, main group 1, has 1 valence electron. Guess what? Any element in group 2A has 2 valence electrons. I'm going to abbreviate, 2 valence electrons. Well, none of the elements in group, the B groups are considered main groups. So I bet you're asking, well, how many valence electrons do they have? The answer here, and I actually forgot to say this morning, these all have 2 valence electrons, okay? So everything in the transition metals, main group, or sorry, not main group, but group B, they all have 2 valence. So we're going to skip over those. We're not counting those. We're counting the main groups. So we're going to come over here to main group 3. These have 3 valence electrons, so on and so forth, till you get over here to 8, and then it suddenly stops. This is the max. We have 8 valence electrons with the noble gases. And there's a reason that it stops. There's a reason that's the max. We'll talk about that as well. Okay, questions on how you count valence electrons. So if I pointed out any element and I said, tell me how many valence electrons it has, I would want you to be able to do that. That's critical, that's key, okay? So let's go back up here to fluorine. So now that you know how to count valence, how many valence electrons does fluorine have? Seven. Thank you, Tyler. So draw those on there. 7. 1, 2, 3, 4, 5, 6, 7. All right, so there's fluorine. Now, yes, there are electrons on that first inner circle in fluorine, but we're not talking about those electrons. We're really just focusing on valence right now, okay? But don't think that that's all the electrons in fluorine. Those are just all the valence electrons, the outermost. Okay, let's draw chlorine. How many layers to my chlorine atom should I draw? How many energy shells? It's on row 3, right below fluorine. So I'm just going to draw an extra row there, or an extra circle. And how many valence electrons does it have? Guess what? It's in the same main group. So yeah, 7 again. So draw those on there. So that's chlorine. Bromine, guess what? Right beneath chlorine. So it gets 4, 1, 2, 3, 4. It also is a halogen, which means it has 7 valence electrons. It's in main group 7. So there we go. So these are pictures of these elements, and I just wanted you to see that they all have the same number of valence, and they all have similar chemical behavior because they're all halogens. All right, so there's a relationship between the number of valence electrons you have and what group you're in and how you behave in nature. So elements that have the same number of valence electrons tend to have similar group properties and chemical reactivity, okay? That was the whole point of that. So do you feel confident in counting valence? For any element, you could tell me on the periodic table now how many valence electrons it has. Anybody?
How did you say we find the layers again?
The rows. So
Oh,
you look over here, we're going to number the rows. 1, 2, 3. As you go down, you increase the row number.
oh, yeah, okay.
7. So you look at what row it's on. That's how many layers you should, how many circles you should draw around the nucleus.
Okay.
Great question. Oop. Okay. Now, why? The question is why? Why, if they have the same number of valence, do they have the same chemical properties or similar? The reason is valence electrons, first off, remember they're the outermost electrons in an atom, and therefore they are the most loosely held, right? They are the most loosely held. What do I mean by that? Well, remember that, let me scroll back up to my picture. For example, bromine. Here is the nucleus of bromine, right? And we know there's a lot of plus charge. In fact, how many protons are in bromine? Can anybody tell me? How many plus charges are packed into that little nucleus? $35 question mark? Yeah, I think that's the number. You just look at the atomic number right here, 35. So there, I could draw them all out. I'm just not going to take the time. There's a lot of plus charges, right? There's a big magnitude of positive charge. And sorry, I didn't mean to zoom in like that. The electrons, let's say, I'm going to draw it in black. The electron on energy level 1 is really close to the nucleus. So it's going to feel that attraction from those protons a lot. So it's going to be pulled really hard towards the nucleus. But as you go out, 1, they're just further away. And then 2, you have a bunch of other electrons on these inner levels shielding. They kind of act like a shield. And they shield some of that pull from the nucleus, some of that positive attraction. So that's why we say these valence are the most loosely held. They feel the positive attraction of the nucleus the least amount. They still feel it in each atom, but they're the most loosely held for that reason. Right. Now, continuing, all atoms want to have a full outer shell of, guess how many? 8 valence electrons. And this right here is really, really, really key. In fact, in chapter 3, we're going to have its own rule. It has its own rule in science, and we'll tell you what that rule is in chapter 3. But just know for now, all atoms want to have a full outer shell of 8 valence electrons. There's something stable, there's something satisfying when you have 8 electrons in your valence shell. Okay, so because of that, atoms will give away or receive valence electrons so that they get 8. Let's look at some examples. So for example, the halogens, we just drew it out. They have 7 valence electrons. So what are they gonna, yes, Tyler, it's the octet rule. I just saw in the chat. What would the halogens want to do to get 8? How are they gonna get 8?
Take 1.
They want to receive an electron from someone else. It's got to come somewhere. Remember earlier how we said group 7 likes to interact with group 1? Guess what? Group 1 elements love to give 1 electron away, and just 1, only 1. And so that's why group 7s tend to like group 1 elements, because they have the right amount of electrons they're looking to trade, okay, so that everybody gets an octet. All right, for example, an atom with 5 valence electrons. Somebody give me an example of what element this could be. An atom with 5 valence electrons. What element could I be talking about? Matt says nitrogen. Summer says, yeah, nitrogen. Because it has 5 and it wants 8, it will receive 3 more. So it needs to go interact with some other atoms that are looking to give away electrons to receive 3 more so that it can achieve the octet or the 8. Bailey says, what about group 8? Since they have all of theirs, what do? This is why group 8 doesn't like to react with anybody, because they're like, don't come trying to get any electrons from me. I don't want to give anybody any electrons, and I don't want to take any electrons from anybody else. So that's why we say they're inert, okay? Does that answer your question, Bailey? They just don't react. They can react, okay? They can participate in chemical reactions. They just don't like to. All right, for another example. So this is an example of how an atom will receive electrons to get the octet, but remember we said they can give away or receive. An atom with 2 valence electrons will tend to give away those 2 to achieve a set of 8 in the shell underneath. Okay, what does that mean? Let's look at an example of that. Let's take calcium. Calcium is in main group 2. So calcium has 2 valence electrons. How many shells does calcium have? I'm going to draw a picture of calcium. Here's calcium right here. Okay, it is on row 4. There we go, thank you. So if I draw the nucleus, and then I draw 4, 2, 3, 4, there it is, and then we've got 2 valence. We said calcium will give away those 2, and it should have a full shell underneath. Okay, so what we haven't been drawing is all the electrons on the inner shells. So when calcium gives away 2, it literally, that outer layer goes away. And what it will have is a set of 8 underneath. And then it's stable. Okay, so it'd rather give away 2 than gain 6. The path of least resistance. Okay. All right, so we've done a lot of talking and thinking. Here's kind of the summary. It happens that elements within the same group, we've been talking about that. How do you identify a group and all the elements in that group? Elements in the same group have the same number of valence electrons, and this is why, and they therefore trade electrons in a similar fashion. This again reinforces the idea that they have similar chemical properties. And the reason why they behave the same way is because they trade, give away, or receive valence electrons the same way. Okay. So guess what? I'm going to go back up to the periodic table. We have a little bit of time. Everything, I'm going to draw a big line. I'm going to make this line really thick. I'm going to draw a big line right here. I'm going to divide this periodic table into 2. Everything that is left of that line, every element, do you think it's going to want to give away or receive valence electrons to satisfy the rule of 8? Yes, thank you, good. They're all going to want to give away, all right? These, I can't write that, but I'm going to try to do it, give away. Every element on the right side, except I'm going to mark out group 4. Why? 6 one way, half a dozen the other. You've got 4, you could either give away 4 or get 4 more, okay? So we really don't see group 4 elements trading electrons. They do something else. We're gonna skip over them for now. We'll come back to them. But everything right of the line, except for group 4, is gonna wanna do what? Give away or receive electrons. Yeah, Haley said it, take. They're gonna wanna receive electrons. Oops, sorry. Receive electrons, okay? All right, let me take this back down. Questions. Okay, these are some trends to know. This is going to help set you up really good for chapter 3, which we'll get into on Thursday. So lastly, we're going to talk about electron dot structures, and we'll do a quick practice problem. And then I'll show you, I have some practice problems from the back of chapter 1 that I want to work. So we're going to work a few. These are more complex conversion problems. You need to be practicing these as you get ready for exam 1. So we're going to do a couple together, and then that'll conclude kind of our stuff for today. All right, electron dot structures. This is just a way to represent elements so that you can quickly identify how many valence it has, okay, versus looking at a periodic table and counting, and it's just a quick visual. So it's just you write out the symbol, okay, so here's the main group numbering, 1A, 2A, 3, all the way to the noble gases. And you can see we've written out the dot structure for all these elements. So you just write the symbol. For example, hydrogen. You write the symbol and then you put a dot that represents how many valence it has. So anything in group 1A is going to get 1 dot. So all of these have just 1 dot. And then as you go across, 2A, 3A, 4A, you add a dot to represent the number of valence. So for example, skip over to 4A. We've got 4 valence electrons in carbon and any other element in the same group as carbon. So they get 4 dots. And the rule here, there's sticklers on this. You put 1 dot on each side before you pair up dots on a side. Okay, let's write those out. Let's just do these first two, A and B. So I have these elements. I want you to give the number of valence electrons and draw the electron dot symbol for these top 2 elements, Kr, and then C is carbon. So go find how many valence they have, write that out, and then draw the dot symbol for that. I went down the wrong pipe. Dot symbol, by the way, dot structure, same terminology. Okay. Kr, krypton, how many valence electrons does it have? 8. Good, it's a noble gas. So how are we going to draw that dot structure? Kr, start putting electrons on every side. We've got 4 now, but we need 8, so keep going until you get 8. You should never have more than 8, okay? That's the max. All right, what about carbon? Yeah, 4. Okay, so then we'll draw the symbol for carbon, and just like on the table up the top, you see it looks like this. Okay. All right, questions with valence electrons. This is a big deal. If you are confused on valence electrons, please reach out to me before Thursday. Honestly, reach out to me today or tomorrow so we can straighten that out, because Thursday we're going to hit the ground running with how we trade electrons and what that forms and charges on atoms, and it's a bunch. So please do not let this float, or just please address it if you're confused on any of this. All right. Let's work some problems together. So grab some pen and paper, grab your calculators, stretch for a second. Please engage with this with us. Please don't just watch me do this. That's not going to help you. I want you to try to work ahead of me. So we have a problem here. Again, this is found in the back of chapter 1 in your textbook. It says drug dosages are typically prescribed in units of milligrams per kilogram body weight. All right. Milligrams per kilogram body weight. You're familiar with this anytime you take a Tylenol or any sort of a pain pill or any kind of medication. There's a prescribed dosage with it, or there should be. It says a new drug has a recommended dosage of 9 milligrams of the drug per kilogram body weight. That's what they recommend you take. So if you take more than that, you could be taking too much. If you take less than that, the drug might not be effective, right? Question A, or part A, says how many milligrams would a 130-pound woman have to take to obtain this dosage? So I'm going to give you a minute. Read it. Try to figure out, where do I need to start? What is my question asking for? What units? And then I'm going to come behind you and we'll work it out. Okay, what is our question asking for? What units do we want? Okay, yeah, read closely. It says how many milligrams? How many milligrams of drug? And remember, milligrams, sorry, Bailey, it's just a technical thing. That's a lowercase m. It should be, so we're looking for units of mg, lowercase m, in our answer, all right? How many milligrams of the drug does this woman need to take? And she's 130 pounds. So somebody tell me, where do you want to start? Where could we start with this? Pounds to kilogram, convert to kilogram, convert pounds to kilogram. Okay, I'm seeing a lot of people convert pounds to kilogram. If that makes sense to you, great, do it. Here's where I recommend you start. We want milligrams in our answer, so do we have anything that the problem gives us that has milligrams in it? Yes, we do. I circled it right up here. We have a recommended dosage, okay? And so she's got to take that recommended dosage. She's got to take 9 milligrams of drug for every kilogram of body weight. And if we start there, then, so we're assuming that she's gonna take that. So we're gonna start with milligrams on top, and that's gonna put that unit where we want it for our answer. So now we're gonna go about canceling any unit we don't want in our answer, okay? Now, I saw it a lot in the chat, convert pounds to kilograms. That's great. We do need to do that, okay? So you have a 130-pound woman. We need to convert pounds to kilograms. Anybody have a relationship for pounds and kilograms?
Isn't 1 kilogram equal to 2.2 pounds?
Yes, it is. Thank you, guys. So there's the relationship. So you can do this a couple different ways. You could plug this in as a conversion factor, okay, like this, and say for every 1 kg, it's going to be 2.2 pounds. Or if you didn't do it that way, some of you may have said, well, I'm going to take 130 pounds, and I'm just going to go ahead and cancel pounds and convert that to 1 kg, and that's fine, okay? So what is her weight in kilograms if we do it like that down here at the bottom? $130 divided by 2.2. 59.1. We'll just say 59.1 kilograms, all right? So you can do this, and then you need to cancel kilograms and convert to milligrams. So then you could multiply by the dosage, all right, and cancel kilograms. So you write for every 1 kg, it's 9 milligrams. And then you would get the number of milligrams she needs for her weight. So what is 59.1 times 9? 531 point, we're just going to say 0.8. And I'm kind of running out of room, but that should have units of milligrams on it. All right, so that's fine if you wanted to kind of break it up that way. Or if you started up here like I did with the milligrams on top, and then you plug in and you convert kilograms to pounds, now you're just going to multiply by her weight. Because look, you canceled kilograms, and then we also don't want pounds in our answer. We just want milligrams. So if you do it like this, pounds cancels as well. And, you know, we could also mark out how everything canceled over here as well to give us milligrams. So there's kind of 2 ways you could have worked it. Either way is perfectly fine. All right. Okay, there's a part B. How many 125 milligram tablets should a 40-pound child take to receive the recommended dosage? Okay, so similar question, but I think an extra step we're going to have to do here. What do y'all think? I'm going to shrink some of this down and give myself some more space. Well, I don't know if I can. This is a mess. All right, anyways, I'm just trying to create some space down here. Okay, part B. What do we need to do here? What is the question asking for? What's the units on our answer in part B? Okay, I'm seeing some different things. Tyler said milligrams. Kiki says tablets. Keyshawn says divide the amount that they need by how much is in the tablet. Yeah, it's tablets. Okay, so it doesn't directly spell that out. This is how many tablets. Now there's a relationship given to you here. Each tablet is 125 milligrams. Okay, so we can actually write that out. One tablet is 125 milligrams of drug. But you want to know how many tablets does the child need to take. So that's kind of the unit there. So where should you start here? What's the first step? Did anybody work this out? What was the first step you did? Don't be shy. Convert pounds of the child to kilograms. Okay, let's do that. That's what's the common thing people are saying. So you're gonna do 40 pounds. That's how much the kid weighs. By the way, I have a recommendation to whoever wrote this problem. Kids don't take tablets well. Have you ever tried to get a kid to swallow a tablet? So they should put this medication in liquid form and we wouldn't even have to do this, but 2.2 pounds for every 1 kilogram. Pounds cancel out. Now what do y'all want to do? What should I do next? What did you do next? Kilograms to grams. Okay, Kaylee, what would, I mean, and this, you don't have to answer this, but think, we don't have grams anywhere in the problem. So I'm not sure converting to grams would be the best step, but all right, beneath that, Haley said use the kilogram to milligram ratio. So remember, here's the recommended dosage. That's what the child is gonna take, hopefully that dosage. We don't wanna give him too much, or her, whatever the kid is, or too little. So we're gonna plug in that dosage and convert kilograms to milligrams using the relationship of the dosage. So which says for every 1 kg, that child should take 9 milligrams. And we definitely want the child to abide by that. And now we need to cancel milligrams and convert to tablet. And we have this relationship that we wrote out right here to do that. So you're gonna cancel milligrams. So for every 120, I don't know why I wrote an extra 1. So for every 125 milligrams, the kid should take 1 tablet. And you'll notice milligrams cancels as well. So now you do the math, okay? So remember, setting up this all correctly, showing me what units cancel, that's half the battle. If there's different ways you can do this out in your calculator, but you need to start with 40 pounds, divide by 2.2, multiply by 9, and divide by 125. Or you can literally do times 1 divided by 2, but I would put in parentheses if you do what I'm about to do. You could do times and then everything in parentheses 1 divided by 2.2, and then times everything in parentheses 9 divided by, if you want to do it that way, but you don't have to. How many tablets did y'all get? 1.3 tablets. So I'd probably round down and just give them 1 to be safe and see if that helped with whatever the drug was supposed to do. Okay, so we still have a few minutes left. Questions on this problem? This is what I consider a complex conversion problem. Multiple steps, multiple units. Now, again, on an exam, I would give you pieces of information like this right here. You needed that pounds to kilogram relationship, so I would give that to you. I'm not going to go ask you to look anything up on the internet for an exam. Please don't do that. But 1.104, this is another one. And this is an even problem. So the answer to this, if you work this on your own, answer to any even problem in the textbook is you can find that in the back. You can always check your work. So I'll read this problem. In a typical person, the level of blood glucose, also known as blood sugar, is about 85 milligrams per 100 milliliter of blood. If an average person contains 11 pints of blood, how many grams and how many pounds of glucose are present in the blood? All right. Again, I'm going to let you just sit and think on this. I think that's the best thing for you, even if you're struggling with it. Get your brain thinking. Where do I need to start? What's my question asking for? How do I get there? Now, I'll tell you this. There's some information you don't have that you need for this problem. So we may have to look something up. Okay. Anybody want to tell me where do we need to start? First off, I see it says how many, there's our unit. There's actually two questions here. It says units and then separately how many pounds. So first we're going to do it one at a time. How many grams of glucose are in the blood of one human body, one adult, one individual? Where do I want to start? How do we get to grams? Grams of glucose. Tyler says convert milligrams to grams. Okay, so convert pints to milliliters. We will eventually need to do that, Jonathan. Okay, so milligrams to grams. So y'all want to start with the number of milligrams given in this problem? Is that where you want to start? Okay, so let's do 85 milligrams for 100 milliliters of blood. We're going to convert milligrams to grams. So how many milligrams are in a gram? You need to know that. So this is a relationship. You have this in your notes. If you go back to our measurements lecture, there's 1,000, okay? This is one I ask you to memorize because you see how commonly we run into milligrams or milliliters or just milli period. So 1,000 milligrams for every 1 gram. Now, milligrams cancel, we have grams, so we just need to get rid of milliliters, okay? We need to multiply by the volume of the blood to get rid of milliliters. So what can we do here? How do we get rid of milliliters? Yeah, Tyler, you could write 10 to the 3 if you wanted to. How do we get rid of milliliters? We've also got to account for the fact that the human body has 11 pints of blood. So, okay, what's the relationship I'm seeing in the chat? Pints and milliliters. We need a relationship between pints. So for every 1 pint, pint's bigger, by the way, you probably knew that. How many milliliters are in 1 pint? Or you could do milliliters to liters and liters to pints. That's fine too. But I bet somebody, okay, thank you, Keyshawn. Is there any decimal was that? Is it 740? Well, sorry, 473 exactly? 0.0? 0.1? Okay, we'll go with 0.1. 0.17. I like, look at all those decimals. Thank you, Haley. Let's use that. Okay, so now we're going to cancel milliliters. 473.176 milliliters for every 1 pint. And then what do we need to do? So right now we have grams per pint because those are the 2 units that do not cancel. What's the last thing here? Convert grams to pounds. That's for the second question. We're still working on question 1.
The 11 pints of blood.
Multiply by 11 pints of blood. We need to cancel pints. We got 11 pints here, and we need to multiply by that. We don't want to know how many grams of glucose in 1 pint of blood. We want to know how many grams of glucose in the whole body, and that's 11 pints of blood. So pints will cancel. So now you do 85 divided by 100 divided by 1,000 times 473.176 times 11. So I definitely consider problems like this complex conversion problems. For sure, expect something like this on an exam. Okay, how many grams? Anybody got it? 4.4 grams of glucose. All right. Now, this number does not seem like a lot, but considering that one molecule of glucose weighs like nanograms, this is tons and tons and tons of glucose, okay? So, How many pounds of glucose are present in the blood? All you got to do, you do not have to rework the whole problem. Don't do that. Just take 4.4 grams and convert to pounds. You can look up a direct relationship, or if I gave you one on the exam, you could do, somebody said you could do grams to kilograms and then to pounds, because we've commonly done that. So what would that look like? Grams to kilograms, 1,000 grams in 1 kg. And we've done this a lot. For every 1 kg, we know it's 2.2 pounds, okay? Okay. Yeah, we're pretty much at time, so if you gotta go, thanks for joining. But anyways, how many pounds is that? It's probably a very small amount of pounds. Anybody get it? Should be like 0.009, we'll say 97. All right, good. So that does put us at a stopping point for today because we are at time. So I just wanted to do some practice problems. Remember your quiz today.